Alrighty, so this is hydrostatic pressure, which just means the pressure of static water. I guess it's talking about water, but the fact that we have atmospheric pressure is also hydrostatic pressure, and the pressure in the bottom of a thing of mercury, we still call it hydrostatic. But anyway, this is our formula for this, right? And where it comes from is this. Okay, if we've got some container like this, it's got a radius, it's got a height, and on the top it's got an area, right? That mass of water is exerting a force on the bottom of this, right? So the pressure is going to be force divided by area, right? And the force is going to be the mass of that water times g over that area, right? And the mass of that water is going to be, it's going to be the area times the height, right? We'll call the height h, and the area of this thing a, right? It's going to be the area times the height. This would be the volume, right? Times the density times gravity, right? So this is volume times density, which is the mass, right? Times g. This makes it the weight, right? Divided by the area. Now, if you look at that, right? First off, what's that term there where you say that's the volume, right? But then notice that the area of the container cancels. In fact, the geometry of it cancels. All that matters is the height or the depth you are below the water, right? The density of the fluid and the gravity, right? So this is the h is not how high you are above the water. It's the depth of the water, or how far you are down, right? In meters, g is g, right? And this is our density, okay? And I've got some demonstrations that I'll show you next time for this, okay? But ultimately, we end up with pressures rho gh, okay? So let's calculate the pressure. Here's the surface of the ocean. The Titanic is down here below the ocean, 3,800 meters, which is amazingly far below the surface of the ocean, right? And we want to find basically what this does is it finds the difference in pressure between above here and here. Okay, so I'm just going to use this. So the pressure is rho gh is equal to, let's see, what's our rho? Oh, it's seawater, so it's a little more dense than fresh water. So it's 1,025 kilograms per cubic meter, right? So that means that there's 25 kilograms of salt in a cubic meter. And we saw a cubic meter in front of the class, right? In that cubic meter, there's 25 kilograms of salt, which is quite impressive. That's why it's so salty. And then let's go 9.81, and then our depth is 3,800. All right, so this is going to give us in pascals what that difference in pressure is, which it really is what it is. It's the gauge pressure. It's how much higher than atmospheric pressure it'll be. So 1,025 times 9.81 times 3,800. And this is 3820990. Okay, 938. Okay, so 3.8 times 10 to the 7th pascals, because I guess we only have 2 sig figs, right? Okay. Calculated in pascals in psi. Okay, so let's convert this to psi. I'm going to divide by an atmosphere, so 1.013 times 10 to the 5th pascals. This is pascals. That's pascals per atmosphere, right? And then an atmosphere in psi's is 14.7. Okay, so let's see. This divided by 1.013 E5 is 377 atmospheres. That's truly impressive. Okay, so times 14.7. That is 5,544.8 approximately psi, right? That's amazing. Like 2,000 psi in the lab is like danger, Will Robinson. 5,544 psi. You spring a leak and I have no idea what that do. That just saw right through you. Okay, so let's see. PSI and atmosphere. Oh, this was, by the way, in atmosphere, it was 377 atmospheres. Okay, and atmospheres is just this. That's ATM. And here I multiplied ATM by an atmosphere in PSI. Do we answer all the questions? Oh, okay, and why is it gauge pressure? Because basically what we did was we found the change in pressure from here to here. So this is that much more than the actual pressure, right? Now, if you wanted to find the absolute pressure, you would have to add the atmospheric pressure. So the absolute pressure would be, this is our gauge pressure. And then we'd have to add, all right, is that 1.01 times 1.013 times 10 to the fifth? 1, 2, 3, 4, 5. Yeah, so you could see that in this case, the gauge pressure and the absolute pressure are almost the same, right? Okay, so I'm going to take that number there and add 1.013 times 10 to the fifth. Oops, it didn't like it. Oh, I forgot to say fifth. All right. And it ends up being 383. And that last decimal place, if we had 3 sig figs, you could just barely see the difference. 11250 pascals. That's the absolute pressure. Okay. So this is just an example of this, and we did a lot of things with it, but basically this is our answer. This is all we really need to be able to do is get that. Let's look at an example where we have this thing. So this is actually in the data packet. They give you this formula. Okay. So this is like what the absolute pressure, right? The absolute pressure in pascals. That's the pressure above the fluid in pascals. And then this is our rho GH. And that F is the density of the fluid, I guess, right? So it says, at what depth below freshwater is the absolute pressure 100 psi? This is too difficult. All right. So what I'm going to do is I'm going to turn 100 psi into pascals, okay? I don't know what to do, so I'm just going to do that. So 100 divided by 14.7 times 1.013 times 10 to the fifth is equal to, so this is I'm converting to pascals. So 100 divided by 14.7 times 1.013 E5. And I get that's 689,115.6 pascals. Okay, and now I can use my nice formula there, right? Okay, so this is, I guess, assuming that there's one atmosphere above this water, right? Okay, so here's our density, right? Here's our pressure naught. So let's just set this up, right? P is equal to the pressure above the fluid, which would be the atmospheric pressure, right? Plus rho GH, so rho GH. And we'll just stick the numbers in here. 689,115.6 is equal to 1.013 times 10 to the fifth. Plus, and then let's see, this is 1,000 is our density. And G is still 9.81. And then H is what we're solving for. All right, so this is the 100 psi converted to pascals. Right, this is the atmospheric pressure. Okay, so that's what we use for P naught, right? Ta-da. If it's not atmospheric pressure, right, by the way, if they tell you some pressure, like it's in a tank, then use that pressure. And now we're all set. So I'm going to take this, I'm going to subtract 1.013 E5, and I get now 5,87815.6 is equal to 1,000 times 9.81 times H. And now I can solve this, right? So divide by 1,000, divide by 9.81, and I get 59.92 meters. And I just chose 100 psi because I know that's good and dangerous, right? An air compressor at 100 psi can actually damage you a little bit, you know. And if you go 59.92 meters, which is a long way, right? That is times 3.281. That's almost 200 feet down, right? There's 100 psi of absolute pressure pressing on you. All right. So try out, the next videos will be some example problems. Just try those. If you can solve it without looking at the videos, go ahead and do it. If you can't, watch the videos.